Hey guys, welcome back to another video on this series on Halide. So in this video, we will start talking about schedules and we will see or look at some simple schedules. Before I jump into schedules, I'm sure you have seen me struggling through getting Halide up and running in Windows, and I wish I had taken a look at this README on Halide and CMake. So this basically walks over how to use CMake and compile and package Halide from source and basically how to get things running. I wish I had taken a look at this instead of figuring out things on my own. So if you want to take a stab at this or take a stab at Halide on Windows, follow this README file. It's very well written, and this was pointed out to me in the comments by Alex, who is also the maintainer of Halide. So it's a pretty good document. Another thing is you should also watch the CPPCon video on Halide by Alex, which is far better than my videos will ever be because it's done in a very professional manner and he explained things very nicely and much better than I could ever do. So definitely take a look at this video, and also there are two more Halide videos, one from CVPR 2015-16 and there's another one that talks about generators and how to optimize your Halide pipelines. So definitely check those out. So this one is the Halide CVPR. Um, yeah, so that's that. And also, so I do not come from compilers or optimization or a heavy computer science background. My domain of specializations are deep learning and physics. So I will. So this is a learning process for me as well. You know, I'm making videos while I'm learning myself. So maybe I will make mistakes and I might say dumb things. So feel free to correct me in the comments, and I would highly appreciate that because I'm here to learn as well. So thanks, Alex, for the comments. I don't know if you're watching, but thanks. Um, all right. So with that out of the way, we will jump into scheduling. And for this video, I will talk about just single stage pipelines. What that means is, let's say I have some, um, so let's see, how do I explain this? Okay, let me take the blur example. Let's say I split my blur operation into two stages, where in the first stage, I apply blur along the y-axis, and then the second stage, I apply blur along the x-axis. So if you combine these two, this is a blurring operation. But then this has been split into two stages. Typical algorithms and typically what you're going to do would be a multi-stage process. So that requires certain other trickery to deal with. That's a slightly more complicated case. So we will not get into that. We will talk about some single-staged pipelines like brightening operation, where all you're doing is adding a number to each pixel. So this is good to get started with, and that's why I will choose the brightening operation and try to like play around with different schedules. Now, before I get into that, Halide has a pretty fantastic, I mean, at this point, I don't know why I'm making the video because this scheduling tutorial, lesson number 5 that they have is pretty fantastic, and it has some nice GIFs to tell you what the different order and orientations are. So definitely take a look at this tutorial as well. Okay, so um, let's jump back, and on my GitHub page or this GitHub repo, I have posted uh, basically the code and some notes for scheduling the brightening operation. So let's jump into it. And for this, we will be using the same code as before, the brightening code, which basically all it did is it added a factor to each pixel. So the value corresponds to pixels in my input, and then it added a factor to each of them, and then it clamped them between 0 and 255. So that's your standard brightening operation. Now, one thing to note is when you call realize, So when you run the program and it hits realize, that's when Halide JIT compiles your code. So this is not compiled ahead of time. This is compiled, right then and there in a JIT fashion. So that's one thing to note. And also, you need to pass in the dimensions of your image because the computation graph is formed end to front. So from the output to input, that's how the computation graph is formed. And you pass in the width, height, and channels of, or the size of height, width, and channels. And also, we will be timing this operation using Chronos. So that's that. One additional thing that I would be doing is I would print the loop nest. So what this does, it basically, so the usage is func dot print loop nest. What it does is it prints out the order of the loops. So this gives you a good idea of like how the loops are getting evaluated. It's just to elucidate what's going on. So, okay, let's see how this whole process looks like. So in the original evaluation, um, so I haven't done any scheduling. I'm just directly calling realize, no reordering, no fancy business. What's going to happen is I would have three for loops, and these three for loops are in this fashion. What's happening is first I'll get a for loop for the channels, then I'll get the for loop for the height, which is the y, and then the for loop for the width. So y is this dimension, and x is the width, y is the height. So for channels, and then for y and for x. Now, if you just look at these two loops, it's a row order evaluation because um, for each row, I am looping over all the columns. So I'm going row by row, which is the most efficient depending on how your memory is laid out. But by default, Halide is row major. And I get some timing. Now this will turn out to be slowest. And the reason for that is, uh, let's see, how do I describe this? Let me bring my notepad up. Okay, my notepad's here. Where'd it go? Right. So images are stored um, in a row-wise fashion, and then all channels occur together. So I would have, let's say for the purpose, I have a 2 by 2 image. So I have R 2 by 2 image of three channels. So I have RGB values, and then again an RGB for the second pixel, then RGB for this and RGB. So in all, um, in memory, this would be laid out one in one line, but here I have split it into two for just to explain what's going on. This is the y-axis and this is the x-axis. Right now, when I am reading, um, so when I am looping, so that's why reading. Let's see, how do I want to explain this? Okay, so first of all, in this case, if you see the channel is the outermost loop. So for each channel, so I'm going to read channel at a time, and then I will proceed in a row order fashion. So the way that I'm proceeding is, let's say when I go for channel red, I read this R, and then I have to jump ahead to this R, and then I have to jump ahead to this R, and then I have to jump ahead. So there's this redundant jumping is a costly operation. Well, it's not costly on its own, but then like when there are multiple jump operation, it becomes costly. Infinity times zero, well, I'm making stupid examples, but then a very small number times a very large number is a constant, right? So it's a big, decently sized constant. So you don't want this jumping. You don't want this jump to be happening because all I'm doing is adding a factor to each pixel. So why should I care about whether I'm reading red or green or blue? I should just go sequentially. That way I don't have to jump. So what if I reorder my loops and I put the channel at the very end. So for each um, pixel location, I would read through the channels. I'll go RGB, go to the next one, RGB, go down, RGB, and then next RGB. So that would be the most efficient way of reading memory. And that's the next step that we will do. So let's get rid of that. Okay, so basically we will reorder loops. And reordering loops can be done by a simple command. So all these scheduling commands require you have this format func dot whatever you're trying to do. So reorder basically reorders my loops. It's inner to outer. So this tells me, so I'm telling it make C my innermost and then X and then Y. So this is what I would see. So, and when I run this, so the original time, so these timings were on a separate Linux system, and so this was about 430,000 or 430 milliseconds, and this became 80 milliseconds. So that's like an order of five improvement, not order of five, but a five times improvement. So you can see this is far more efficient. And the for y and for x looks like this because it's row major. So I read a row at a time, and then I go to the next row. I read it, and then I go to the next row. Um, these images I have taken from one of the Halide papers, and yeah, so this is the paper from which I've taken these images. Anyway, so that gave you an advantage. So that's reordering loops. So you can see just by reordering my loops, I got five-fold speed up. So that's pretty crazy. All right, so let's look at the next operation, tiling. So tiling is a very common operation in which what you do is you break each loop. So ideally, so what tile does is it breaks both the loops, the y and x, into an inner and an outer loop. So what that basically does is, so when I break both my for loops, both my x and y axis loops, it will break my grid into smaller grids. So my large grid, I would tile it up. That's why tiling. So I will break it up into small grids. Now, at this point, this is just a reordering that's happening. Like I'm not doing anything fancy to it. All I'm doing is breaking for loops. But on its own, tiling it doesn't do anything. Just breaking the loops, it'll probably be a more costly operation. But later we will see when I combine tiling with, say, parallelization and vectorization, that's when you start seeing advantages. So what I can do is I can tile up my whole grid and I can send different tiles to different threads. So that's when you will start seeing speed ups. So at this point, tiling is just breaking up for loop into an inner and outer. So let me show you in this case to break it to break to tile my func. I call it func.tile, and then I pass in my uh, the loops that I want to tile or the variables that I'm looping over to tile x and y, and then what do I want to call the outer and inner? So I call them x outer, y outer, x inner, y inner, and then how much do I want to tile them by? So my tiling, so I'm breaking them into grids of 4 by 4. And then I call the reorder function again because I always want my C to be the innermost operation because I want an efficient read. So the order of execution in this case becomes this. So for y outer and for y x outer, I want the outers to appear at the outset at very outer end because um, they control the number of tiles, and I again want them to be read in a row-wise fashion. And then the inner loops are also read in a row-wise fashion, but they go over from 0 to 3 because I have set my tile size to be so and so. And then finally, I have my C loop. So uh, at the end there would be what did I do? So at the end, sometimes you might not be able to tile up my entire grid completely. So there are some various strategies to deal with it, but we won't get into those at this moment. Excuse me. So this 4x4 tiling looks like this. So this is the inner loops that are working, inner loop, inner loop, inner loop, inner loop, and jumping between tile 1 and tile 2, tile 3 and tile 4 is what is dictated by the outer loops. And we go in this fashion because we want to read everything in a row-wise fashion. Um, as we will see, just doing this increases the time of operation because I'm inducing jumps in my code. So, or memory jumps. So, and we haven't done anything fancy. Now, now we will do something cool, which is vectorization. So before, so I'm just gonna read the line that I wrote because it's nice. Vectorization operation transforms loops into sequences of vector operations. It is basically a process of rewriting loops so that instead of processing a single element of an array n times, it processes four elements of an array simultaneously n over 4 times. Um, okay, I thought in my head, I thought this would make sense, but it kind of didn't. So let me explain vectorization with, oh, in my notepad. Give me one sec to, oh, there's, right. So let's say I am adding two vectors and let's see, 2, 4, 6, 8, 10, 12, 14, and 16. That's vector A. And in vector B, excuse me, I would store the odd 1, 3, 5, 7, 15. Okay, so what's the naive way of adding them? Naive way of adding it for I in basically length of A, because the lengths are the same. I'm writing pseudocode. I would do, let's say, C of I equals, yeah, oh, C of I equals A of I plus B of I, right? That's that would be your for loop. That's cool. So in this, so this is not a vectorize operation. I am looping over each element at a time, and I'm doing this operation. A vectorized version of it. So vectorization kind of depends on the hardware because what vectorization is telling you is that your hardware can process more than um, one element at a time. So that depends on the bits, what data type you're using, and whatnot. So let's say my hardware can do 4 ints in one go, or 4 floats in one go, or so on, whatever it is. So in this case, let's say my hardware can process 4 ints or 4 integer operations in one go. So a vectorized version of this code would look like, so this is 4 plus 4, so I need two operations. And then some, basically I'll have to C load 4 and add a comma B. I would have to keep track of uh, whatever the first four indices are, and so basically it's like calling a function that will load 4 elements of A, 4 elements of B, and just process them together and then dump them into C. So I only need two for loop calls. I don't need to I save the increment operation, and then I don't need to jump because I don't need to iterate over each element, and also it's faster because I just need two operations because it's all vectorized. So this is like calling this function that adds four loads and adds four at a time. So that's basically what vectorization is. Um, well, you'll find much better explanations online, but I think this is good enough. All right, so this is how vectorization looks like. Um, uh, in our tile example, I can just quickly vectorize. I can process data in a vectorized fashion, do operation for my vector length, move on to the next, do the operation on a vector length, and move on to the next, and so on. So this will make your code more efficient and will execute in a smaller amount of time. Parallelization is basically if you have two simultaneous operations, you can send them to two different threads and they will compute. They will perform the compute. So parallelization is kind of you know what it is. So in this, I have combined both operations. Actually, let me show you a GIF from the original tutorial on parallelization. So this is how vectorization looks like. You see, um, four grids are processed together in one go. So it's doing four at a time. So that's how vectorization works instead of doing one at a time. Um, I'm sure there would be a parallelization. Oh yeah. So this is parallel example in which there are four tiles and you can see like so this grid, this grid, this grid, and this grid are being constructed simultaneously. So this is how parallelization works. So again, more efficient. Now, in our example, we will combine them. So again, this is not the most efficient way of doing things. It's just some dumb way that I came up with. And the assignment is to, with what we have discussed, can you figure out a way, an even faster way of doing things? So what I do is first I split. So tiling worked on two dimensions. Split works on a single dimension. It's the same thing, it's just that we only split one dimension. So if I apply split operation twice, that's tiling for you. I wonder if tiling can work on dimensions greater than two. I don't know the answer to it, but I'm sure I can figure this out. Because let's say I was doing some deep learning computation in which I have tensors of, excuse me, of dimension 4 or 5. In that case, um, I don't know, maybe useful to have tiling more than two-dimensional. But in any case, split works on single dimension. So if you use split multiple times, that becomes tiling for you. So I split X into an outer and an inner, and I chose a random size 64 for the split, or the grids that I have. Then I vectorize over those inner grids, so choosing my vector length to be 64. Um, okay, so that's that. And right. Okay. And so what what size you choose to vectorize kind of depends on your hardware because so when I say I vectorize over the inner dimension, so my inner dimensions are of size 64 each. So vectorizing over 64 means I will do operations on chunks of size 64. Now this number you should be careful. You should choose according to your hardware. Basically find the instruction set and see what's the size of your operations and then find the data type that you're using. So we are using int 8 here, and which is 8-bit, and then do the math basically. And then so I vectorize over that x dimension. So and then I will parallelize over the channel dimensions because channels are kind of independent. So I will take channels independently. All right, so the order of execution looks like this. So first of all, at the on the outset, I have three threads for the different channels going out, and then I have a for why, because by default it's a row major operation, and then an outer loop, and the inner loop is vectorized. So that is pretty much it. And with this, I get an execution time of 73,000 or 73 milliseconds, which is slightly faster than the reordered loop, which was at 80. Well, there's always a margin of error, but yeah. So that's pretty much it. Now, these are the tools that you would use. There are like few more aspects of scheduling that come into play when you have multi-stage pipelines. But it's basically everything is at the end of the day a mixture of vectorization and parallelization, and when and where you're evaluating things. So we will see multi-stage pipelines in a different video, but I think um, this is a good stopping point for this video. And if you feel up to it, try optimizing the code and see if you can get some better values. I will. Oh, okay. Yeah, let me try running this piece of code on my system. So if I go back, I have the code over here and the makefile as well. Unfortunately, I was too lazy to write a better code, so I just copy pasted the function a bunch of times, and then I just added my scheduling code over here. So um, probably have to refactor this code at some point if and when I get time. But but it works fine. So for now, let me just run it. Okay, give me a moment. Okay, so basically I have, it's pretty dumb. I have like four or five functions which are the same, and except that I jam in the scheduling code. So in the original one, there is no scheduling code. In the reorder, I reorder the channel loop to be internal. In the tiled one, I do the tiling manually, and then I have finally what I talked about. So let's try with a different size. Let me just do it again. Let's try with 64 first, and then in the main, I call all these four functions. So let's run it and then see the timings. Okay, so I'm also printing out the time in milliseconds, and also I am printing out what do you say, the loop order. So this is the original reordered, and then this one is a tiled one, and then the vectorized one. So original, so the in the between original and the reordered one, there's a five-fold reduction. Tiled goes up because I have multiple for loops, and then this parallelized and vectorized one is slightly quicker, but it's still not as fast as reordering. Now, there are multiple factors that come into play. I haven't written the most optimized version of it yet. um, 64 might not be good for my hardware. And also, there is an inherent overhead associated with vectorization and parallelization. So, because this is such a simple operation, not doing it makes more sense and it's much quicker. Let's say if I was doing a multi-staged pipeline, or if I was doing some multiple comp or highly complex computations, or my image size was like 10 times this, then I would start seeing advantage of this technique. So right now, for this small image, I think just basic reordering is the fastest. Let me actually change my vector dimensions. So let's try 32. Mhm. Let's see what I get. Oh, again, like because I'm just running it once, doesn't make like these timings kind of are redundant, because to properly time things, you need to run them a multitude of times. So yeah, so this is basically what I get. And I also wonder, there's another thing that I wonder is what's the difference, like if I did some ahead of time compilation, would it be quicker or not? Might be, because I saved that overhead. But again, these things we will see in later videos. I hope you enjoyed this video, um, and definitely check out. So let me also pull that up. Check out my GitHub page. Where is that? Yeah. So check out my GitHub notes. The code is stored there. I'll send a link for it. I'll post a link for it in my YouTube description. Check out the Halide CMake README and also check out these videos. All right. You guys have a great day. See you later.